Okay, so the next speaker after the coffee break is a freelance Python developer with a huge interest in test-driven development and concurrent programming. And here it is. Thank you.
Thank you. Okay, so my name is Goran, and as you already heard, I'm a freelancer. I come from Croatia, that's right across the sea from here, and I'm interested in concurrent, parallel, and distributed systems, and that's what we're going to talk about here today. So, a brief introduction on what exactly I'm going to be speaking. So, I would like you to have a basic understanding of what something is, and when you should use something, when you should not use something, because a lot of times today people just have some problem, Google something, just put something in your settings files and something, and just if it works, it's good. So I would like for you to have some basic knowledge of some concepts so you can make better decisions, or even if you can't make decision, have some background to do further research. Also, when I use concurrency in this talk, I'm talking about concurrency as an execution model, not as a composition model. So what that means is that in order for your programs to be able to run concurrently, they need to be concurrently composed. Unfortunately, that's way outside of the scope of this presentation, so I'm not going to be able to speak about concurrent composition. We're just going to be focusing on concurrent execution. So what I'm not going to talk about is there won't be any turnkey solutions here. So what it is install this package and put this in settings file, and you're going to get like 50% speed up. There's not going to be something like that here. So if you came for that, yeah, bummer. Also, I'm not going to be talking about GIL. I'm sure you've all heard of GIL and you know what that is. I'm just going to have a single slide where I'm going to describe what exactly GIL is and why is that not a problem for us. I'm not going to be talking about any details. So each of the concepts I'm going to describe in this presentation can be a talk on its own, and it would be a really long presentation if I would go into details on how stuff work under the hood. So I mentioned some buzzwords, and buzzwords are actually cool as long as you know what they mean. So here are some. Take your time to go to read these. So we have concurrent and parallel execution, cooperative and preemptive multitasking, CPU-bound and IO-bound, and thread-based and event-based concurrency. Okay, so I'd like to get some feel for you guys here. So can I get a show of hands who knows the difference between all of these? Hands up. Okay, we got some. I guess most of you are going to learn something today. Also, one more interesting thing is that can I get a show of hands who has used Greenlet directly? And by directly, I mean they typed import Greenlet and did something with that. Wow, the three of you, really? Okay, cool. Actually, there's a reason behind this, so we're going to talk about that as well. Unfortunately, we have to do this part. So what's parallel execution? That's basically executing something simultaneously. So if multiple tasks are executing at the same point in time, that's parallel execution. It's obvious that you need to have multiple CPUs in order to do that. Okay, so this is really simple. Concurrent execution is a bit complicated concept. So that basically means executing multiple tasks in the same time frame. So, but it doesn't have to be at the same point in time. So what I mean by that, let's say we have a time frame of 1 second. Your laptop probably executes a single CPU core on your laptop, probably executes something like dozens of threads in that amount of time, but a single CPU core can only execute a single thread at any point in time. So that's concurrent execution. It doesn't have to be, you can do that with a single CPU core, obviously, and it doesn't have to be at the same point in time. So it just means that multiple tasks are executing at some time frame. So what's so cool about concurrent execution? It's not that we want it, we kind of need it, because we're always going to have more tasks to execute than we have CPUs. Also, up until a couple of years ago, we only had like single core CPUs, so everything was running concurrently there. One more example is For instance, why is concurrency good? Because concurrent execution. Because let's say we have a program that makes an HTTP request to, I don't know, Google, and it takes around 50 milliseconds to make that request and get the response back. We definitely, in that 50 milliseconds, modern average CPU can make tens of millions of instructions, and we don't want CPU just idling there while we are waiting for our response. So we obviously want CPU to execute something else, and then when our response comes back, resume our thread, and we're running on. Okay. Also, CPU, as I just said, is much faster than anything else. So CPU, typical web request takes like 50 milliseconds. CPU can run much faster than that. In my previous definition of concurrency, I said executing multiple tasks in the same time frame. So if these tasks are threads, then we have something called thread-based concurrency. So as I said, that's basically executing multiple threads in the same time frame. What's interesting here is that the OS kernel acts as a scheduler for these threads. So OS basically decides which thread is going to run when and for how long. And this is really interesting, and we should remember this, is that threads, there's really no way for threads to decide when are they going to run. How exactly OS does that? Well, there's the exact algorithm on how OS switches threads. Is really complicated and it's implementation dependent, but two things are really interesting for us. When a current thread does I/O operation, so for instance when our program makes an network request, OS is going to suspend our thread and let other threads run. So this is cool. It's not that CPU is waiting on anything. Also, when the current thread used up its time slice, so OS scheduler internally keeps up like a reference table for how long each thread has run. Also, there are things like priorities. So some threads have higher priorities, obviously, than other threads. So it's really complicated. We'll mostly be interested in the first bullet here. And what I just described, when OS schedules threads to run, that's called preemptive multitasking. We're going to have something called cooperative multitasking a bit later. So just remember that OS scheduled threads, and that's called preemptive multitasking. Most modern operating systems work this way. So the OS decides which thread is going to run when. And the fun fact is that Windows didn't work this way. It works some other way, which we're going to get described later, up until version 95. So Windows 95 introduced this here. Also, older versions of Mac OS, I think 8 point something and 9.2, were not using this. So this was really cool. Let's have a look at this. This is my enterprise application I use for testing stuff. So basically, what I do here is I get contents from 3 URLs, Python.org, Linux.org, and Google.com, and I just print out the length of how many characters are there in their HTML code. This is really, really simple, and this program runs on my server around like 950 milliseconds. This is really cool. And it's the typical example of an I/O-bound program, because most of the time, like 949 milliseconds are spent waiting for something. And I would just like to briefly describe, I'm sure some of you know, but what exactly happens when we run this with Python. So what exactly happens is import executes, our function is defined, okay, cool. And then we get to the first call for get URL. And what happens here is that we get to the URL open call, which is a blocking call. And what happens is that OS suspends our thread and lets other threads a chance to run. So, and when the response from Python.org comes back, OS sees that and gives our thread a chance to run again. Then the program runs again until the next URL open for Linux.org, and that goes on like that. So what's the problem here? The problem is that this is running sequentially. So wouldn't it be cool if there was a way that we could make all 3 requests at once and then just wait, and when the last response comes, our program is done? That should be a lot faster, because this is just, we're waiting for something and then waiting for something again and then again. So if we had like 100 URLs here, this would be really slow. And at this point in time, I'd like to do the GIL thing now. So GIL basically stands for Global Interpreter Lock. And global here means per process. So what that means is that only one Python interpreter can run a single thread at any point in time. So basically, if you have a multiple core CPU and you have your Python program has multiple threads, there is no way that any two threads can run at the same time, no matter how many CPUs have. Only a single thread can run at any point in time. Gil is in charge for that. Even if OS scheduler decides to give your other thread a chance to run at the same time, so that would mean in parallel with the first thread, that's not going to happen. Python is going to prevent that. And now that I said that, I'm going to tell you that that's not a problem for us here. That's only a problem for CPU-bound tasks. Well, why is that? First of all, there's some implementation details that make Gil not a problem for I/O-bound tasks. Also, CPU-bound task, when we have an I/O-bound task, I/O-bound task is eventually going to make an I/O operation, read from disk or network request. So what's going to happen is OS is going to suspend that thread and give another thread a chance to run, and that's cool. If we have a CPU-bound task, that's not going to happen. What's going to happen is CPU-bound task is going to run indefinitely, and it won't get ever a chance to, it won't have any reason to suspend and give other threads a chance to run. So now that I've said what CPU and I/O-bound is, I might as well explain that. So CPU-bound, basically definition says that it's a task that has a property that time to complete it is dependent solely on the CPU speed. So what that means is that if you have a faster CPU, CPU-bound task will execute faster. If you have a slower CPU, it's going to be slower. It's simple as that. So all kinds of number crunching, like also video processing, password cracking, and usual stuff go into this category. Also we have, in contrast to that, we have I/O-bound tasks that does a lot of I/O operations. So anything reading from disk and touching networks and stuff. So interesting thing is that most web applications are I/O-bound. So your typical web application, what does it do? It gets an HTTP request, does some form processing, and then makes a database request or lots of database requests. Maybe contacts Facebook for some authentication. Maybe, I don't know, stores something to disk. Maybe writes to logs. So those are all I/O-bound operations. And the amount of I/O, waiting for I/O in a typical web application is usually much higher than some, unless you're doing an Fibonacci calculation as a service, okay? So up until this point, everything I've said was kind of like a general, the whole OS threading and stuff, it's all non-Python specific. This is a brief overview of how you use threads in Python. We have threading module in standard library, which has really nice functions for creating and managing threads. Also, one thing to note is that Python threads are real OS threads. Okay, so what does this mean now? Does there exist something that's like non-real, non-OS thread? Well, it doesn't really, but there are some things called green threads, which we're going to talk a bit about later. So just remember that Python threads are real OS threads. So, okay, that's all cool, and it works nice, and it's really simple. And then we have a problem. So what's the problem? The problem is when we have lots of threads, and by lots I mean thousands. Oftentimes lots can mean tens or maybe hundreds. The boundary can be lower depending on lots of stuff, what exactly your application does, on your hardware and stuff. So, and before I go on describing what exactly is the problem, you probably are asking yourself now, why would I have that many threads? Where there are use cases that require you to have that many threads, like all sorts of high concurrency systems. I don't know, typical example is chat servers. Maybe you don't have lots of requests, but maybe you have a need to keep a socket open for a longer time, like you're doing some kind of long polling or something. Anyways, there are lots of use cases where you need to have lots of threads. So I did some benchmarks. As is the case with all other benchmarks, is to be taken with a grain of salt. So don't trust everything you see now. I wrote 2 enterprise applications again. First spawns some number of threads. We're going to see exactly how much threads, and where each thread sleeps 200 milliseconds. I'm going to explain just in a bit why did I use those numbers. Second program just spawns also some number of threads and sleeps 90 seconds. So why did I use sleep? It's such a dumb example, but it really serves our purpose here. Sleep is basically an example of I/O bound operation. So I just wanted to make my thread wait for something for some amount of time. I actually wanted to use web requests, but there was no site that would allow me to make 100,000 requests and return me a response every time. So yeah, that wasn't good. Also, why did I use 200 milliseconds and 90 seconds? Well, with program 1, I wanted to test how time-consuming it is to create some amount of threads. I wasn't interested in anything what they will be doing. I just wanted to see how expensive it is to create threads. And with second program, I wanted to see how much memory those threads are going to take up. So here are some numbers for first program. Numbers are really not important. They're going to be important later when we compare them with some other numbers. But basically, you see, this is not really horrible. This is okay. I mean, it takes 2.5 seconds. Also, I tested this on a 8-core machine with 32 gigs of RAM and Linux 3.8 kernel. So yeah. Excuse me? Python version was 2.7.4. Yeah. So basically, you see that we have it takes 2.5 seconds to create 10,000 of threads, which is not horrible. Also, this is not the most useful test ever. Also, it's not really the real-world situation, because if you know that you're going to have lots of threads, you can just create them in advance and keep them in some sort of thread pool. So you can avoid this startup time. And that's why we have this other test, which is really interesting. So what we can see here is that if we create 1,000 threads, that's going to eat up 12 gigs of RAM. These are gigabytes. So this is also virtual memory. That basically means that if all these threads will reference all the memory that they have pointers to, that would consume 12 gigabytes of RAM. There is in the last column, we had a problem here, Houston. So what happened here is that I wasn't able to create 100,000 threads, which is not surprising. I was able to create something in the ballpark of 32,000 threads, and what happened then was my program crashed. So also at that point in time, when I had 32,000 threads running, my program was eating up 256 gigabytes of virtual memory. So as much as I fiddled around with OS configuration and stuff, I couldn't leave that limit in any way. These aren't the only problems threads have. We also have some problems, is that as we've seen, number of threads is limited. You could say now that number of sockets you can keep open is limited as well, but usually that number is much higher, the number of threads, like 10 times higher. So you are going to run into problems with threads much sooner than problems with sockets. Also, people like to say that threads have that preemptive multitasking is actually a problem, and it actually can be a problem. If you have a program which uses multiple threads and they access or modify shared memory, you can run into some weird memory bugs, because you cannot be sure when is OS going to decide that, okay, this thread has run long enough now, here's a chance for this thread to run now. So OS is just going to switch those as it wishes. Some of them might never get a chance to run. So this can be a problem. Of course, you can deal with these situations with various kinds of semaphores and locks, but this is just going to further complicate your application and maybe slow it down. So it's just a trade-off. But then again, what would we like to have? We'd like to have some kind of a thread that will be fast to create, that wouldn't use up all our memory, that would have a property that we could decide when do we want to switch to another thread, or let's call them tests for now. Actually, it turns out we have such things, and they're called green threads. So green threads are not managed by operating system. They are managed by something else, or not managed at all, as we're going to see later. They can exist. We can have lots of green threads inside one OS thread. So since they're not managed by OS, we can just have lots of them inside one thread. Also, they're often called user threads, or lightweight processes, or micro threads, or pseudo threads. And these are not all synonyms for exactly the same thing, but they're often used interchangeably on the internet and literature. So if you see those, it probably means some sort of green thread or lightweight thread. So there are multiple mechanisms that allow us to have green threads in Python. One of those mechanisms is called greenlet. So greenlets are basically some kind of lightweight thread that doesn't have any scheduling. So this is the definition from their website. I've underlined some terms that might not be clear at first, so I'm going to explain them in more detail. Also, one more thing to remember is that greenlets are implemented as C extension. As we're going to see later, that's going to be a problem for us. So they're not like a pure Python module. So about these underlined words, we have first of them is microthread. As we already said, that's just a synonym for a lightweight thread or green thread. Second is no implicit scheduling. That basically means that greenlets are just like a lightweight thread, but they don't have a scheduler. So previously we had threads that were scheduled by OS and all is good, but now we don't have a scheduler. We're gonna probably need some scheduler. We're gonna see about that later. So third word is coroutines, and that's a bit complicated one, so we're going to explain that in a little bit more detail. So coroutine is basically a function that can suspend its execution at any time. So this is really old concept, like 50 years old concept, and it's basically as it says. So you have like a regular function, and that function execute, and that at a certain point in its execution, it decides, okay, I just don't want to run anymore now. I'm just going to suspend. And it hands off control to something other. We're going to see what that is. And then that something else can just resume that thread, that function at a later point in time. And that function is going to continue executing from the point where it stopped. It's not going to start from the beginning. So you can have a coroutine in Python. You can actually use generators to make coroutines. So generators have, you know, the yield keyword. So it's basically a function that has a yield, and yield just suspends the execution at that point, and then you can later resume. So the important thing with coroutines is that they decide when they want to switch. So there is no some scheduler or something that's gonna say, okay, now you're done with running, now you can run. So coroutines decide on their own. So as we're gonna see, this is an advantage and disadvantage at the same time. And this is called cooperative multitasking. And it's called cooperative because all tasks must cooperate in order for this to work. So if a single task is running and it won't give up the control, it won't give up other tasks chance to run, this is not going to work. And we're going to see why is that a problem. So since each task decides when to give a chance for other tasks to run, this is ideal for IO-bound tasks. Why is that? So we have an IO-bound task. It makes a blocking request, like a network request, and then it can just say, okay, I'm done now. I'm just not going to run anymore. You can run now. When that request is done, just resume me, and I'm going to run until the end. Okay, so this is not so good for CPU-bound tasks. Why is that? Because CPU-bound task, as we said, has no reason to give up control of execution. So CPU-bound task is just going to run forever, and it's not going to give other tasks a chance to run. So you can get some weird behavior if you have CPU-bound tasks with this. So now that we know what greenlets are, there's some kind of lightweight threads that don't have a scheduling. We're actually going to see how we're going to use them. And when I asked how many people use greenlets directly, only 3 guys raised their hands up. And this is because greenlets are not that much that useful on their own. You actually need something that will know which greenlet will run next. You need some kind of a scheduler or something. So also, another thing that we need with greenlets is that our I/O operations must not block. So if we make an I/O operation and that blocks, our greenlet doesn't get a chance to give control of execution to other greenlet. So we have to have non-blocking calls. And since we have non-blocking calls, we need something to notify us when our call is done. So the first bullet is called a scheduler. Basically, we need something like a scheduler that's going to have a reference to all of our greenlets and know which one should run next. So we don't want each of our greenlets know about all the other greenlets and then somehow randomly decide, okay, you're going to run next. So we need a scheduler. The second thing is called event loop. And we're going to explain event loop in a bit more detail right now. So what happens here is that event loop is basically something that listens from events from operating system and notifies your application. So all these events originate from operating system. Operating system is the first one to know when your HTTP request is done. It's the first one to know when something you are reading from disk is ready to be used by your program. So operating system handles an event to some kind of an event loop, and that event loop knows which greenlet in your application to resume. So this is cool, but it has one problem, and that problem is that your application is now asynchronous. And so remember the example we had with the 3 URLs. It was really nice program. It was just reading from top down. It was executing top down. It was cool. And now we have a problem that your application is going to look something like this. This is not really horrible because the example is simple, but now we have some callbacks here. So basically a callback is a function you're going to hand over to the event loop. So event loop can know which of your functions to call when the I/O operation is done. Event loop needs to know where to resume your program. And now your program is going to be littered with callbacks. This is not bad necessarily. Some people like callbacks, some don't. I generally don't like them because after a certain amount of callbacks, or if you have like nested callbacks, it gets really hard to follow the flow of execution of the program. So it can kind of make your program not readable anymore. So we don't like callbacks. So what would we actually like? We would like to have greenlets and a scheduler, as we said, and an event loop, so we can run without callbacks. How does that happen? We're going to see that right now. So if we take greenlets and add scheduler and event loop, we get gEvent. This is actually my definition of gEvent. So gEvent is not the only library that does this. There are other libraries that provide scheduler and event loops and using greenlets beneath. One of them is Eventlet. I used gEvent because it's more widespread, I guess, and more maintained. So again, this is an official definition. So take your time to read this. Again, there are some words that are underlined, and I'm going to explain those in a bit more detail. So first of them is networking. I'm sure you all know what networking is, but I've underlined it because I wanted to say that gEvent is not only about networking. It also has some primitives that are useful for local development, like you can use its scheduler to do something with greenlets that's local, that doesn't make network requests. You can also use logs and semaphores that gEvent provides you. You don't have to use it only for networking, although probably like 95% of cases you're going to use it to do something network related. Second is synchronous API, and this is exactly what we told that the problem is with callbacks, is the asynchronous nature of our program. So gEvent is going to enable us to run our program. So our program is going to be synchronous again, and gEvent is somehow going to know where it needs to stop and where it needs to resume, and we're going to see how exactly that works. And the third word is libevent. Libevent is basically a system library that gEvent uses to interact with the operating system to listen for events. So it's just a layer of abstraction upon a layer of abstraction. And so we have OS, and then we have libevent, and then we have gEvent, and then there's our application. Somewhere in the middle of that are greenlets. Okay, this is the same program we had from the beginning of the presentation, the one where we get the 3 URLs, but it now uses gEvent, and the program is actually exactly the same, the flow is exactly the same, except for the gEvent.spawn calls. What that does is basically that creates a greenlet. So we are running inside, this call is running inside a greenlet. What this means is that gEvent spawn first argument is something callable. The gEvent is going to call, and the greenlet is going to start running that function you passed in, and the second argument is just the argument to that function. So we are spawning a new greenlet that's going to run function get URL, and that function is going to get this URL python.org as this first URL. So how exactly is this running if we run it with Python? It runs the same up until the point where we spawn a first greenlet. Then the first greenlet is spawned, and what happens is that greenlet is immediately suspended by gEvent, and the second greenlet is spawned. So all 3 requests are sent at the same time, practically at the same time. So this is exactly what we wanted to have with threads, but we couldn't. so also the last line, gEvent join all, basically what that does is just waits for all greenlets to be over and then ends the program. So this program runs on my laptop around 450 milliseconds. It's about twice as fast as the threaded one. You would even see a bigger benefits of this if you would have more URLs, but this is good enough. Also, this would run even faster if Linux wasn't that slow. I mean, Linux as a site, not as a OS. So, okay, so here are the numbers for our benchmarks. I've added measurements for greenlets. This is not really that big of a difference. I mean, it's not, as we said, if you need lots of threads, you're gonna just create them up front. But basically, we see that greenlets are not that expensive to create. What's really interesting is this here. So I've actually managed to create 100,000 greenlets, and the program was taking up only less than like 900 megabytes. And this is really cool. You can have like really a lot of them, and they're not just gonna eat up your RAM. So how exactly gEvent does its magic? We're gonna see. We're gonna explain just briefly how gEvent does that, and then we're gonna see what exactly are disadvantages of greenlets and gEvents, because the advantages you've already seen them. Okay. So gEvent is doing its magic by monkey patching. We all know what monkey patching is, but basically gEvent replaces standard library blocking calls with the non-blocking versions. So in this case, we have socket get host by name, and that's a standard library call, but it was patched by gEvent, as you can see in the first line. So what basically this does is called the gEvent's patched non-blocking version. So in the background, gEvent knows that you just made this call. It's going to make a call for you, and then when the call is done, it's going to resume your execution from here. So basically, this is some kind of a magic, and this is not the best way to do things, as we're going to see in the disadvantages section. Also, gEvent has an event loop. It uses libevent for that, so gEvent manages all your events. Okay, disadvantages. gEvent works by monkey patching, as we said just a couple of seconds before, but that's actually a disadvantage. Why? So you can only use patched modules. If gEvent didn't patch it, you cannot use it. What's going to happen if you make a blocking request that's not patched by gEvent? That blocking request is going to block our current greenlet. That greenlet is not going to give up control to other greenlets. Our whole thread is going to block, and that's not good. So we are just back to the threaded version of running. So we're not using the benefits of greenlets and running concurrently. So we can only use what's patched by gEvent. This might not seem such a big problem to you, but it can be sometimes if you want to use something that's not patched. So it doesn't work with C extensions. This is a big problem if you consider the fact that most database drivers are written as C extensions. So MySQL and Postgres are both written as C extensions. You can circumvent this by using pure Python versions of those drivers. Then again, if that works for you, it's fine. Greenlet implementation details. So greenlets as I said, are implemented as C extension, and they do some nasty things with stack beneath the hood. So that can be that's not the nicest way to do things. I cannot tell you any immediate problems with that, but when you run into problems, it's going to be very hard to come out of them. It can get hard to debug because of the way greenlets work. So if a certain greenlet called your greenlet and then it was like going all around, and something happens in one greenlet, you're not going to get the complete stack trace. You're just going to get a stack trace from your parent greenlet, which is the greenlet that spawned your greenlet. So sometimes your program can just crash, and you're going to get like 2 lines in your stack trace, and you're going to be like, okay, I don't know what happened here. So that can be a problem as well. What are the alternatives to greenlets? Well, we have Twisted and Tornado, which are both network asynchronous libraries, and they're both callback based. So as I said, this is just a trade-off. If you prefer callbacks, use this. They probably do a lot less magic than gEvent and greenlets. If you like your code to be synchronous and easy to read, use gEvent and greenlets. Also, there are some new happenings in asynchronous world in Python. on this year's PyCon in Santa Clara, Guido announced that he's working on a new specification for asynchronous operations in Python. So basically, PEP 3156 is an attempt to standardize event loop APIs. So the problem is that gEvent has its own event loop, and Twisted has its own, and Tornado has its own. So they can't obviously work together. So this is an attempt to standardize the event loop API. Also, the Tulip, as Guido called it, is an implementation of this PEP. So this is currently serving as a reference implementation, and it's planned that Tulip is going to be in standard library for version 3.4. We're going to see how that's going to work. Also, PEP 3156 and Tulip are not here to replace any of these. They're here to just standardize the interface a bit. Somebody already made a implementation of this PEP that works with Greenlets, so they can cooperate together. It's not like this is going to replace everything. Okay, so here's a brief recap of what we just said. Use concurrent execution. That's going to help you if your application is I/O bound. If your application is CPU bound, concurrency is not going to help you. You need more processes, you need more CPUs. If threads work for you, by all means use that. All of the other thing is just complicating on top of threads. So if threads are fine, if you have like 10 threads or something, use that. They're really easy to work with, easy to debug. OS schedules them. This is just nice. If threads are not good for you, use some kind of async library. I'm not saying use gEvent. Use, if you can handle the hacky background of gEvent and Greenlets, use that. If you prefer callbacks, use Twisted or Tornado. And that's it. Thank you.
So thank you for the talk. And my question is both question and a side note. There's also the kind of new library, concurrent futures, that introduces the thread pool executor and the process pool executor. Mm-hmm. Did you try them, and how do you compare? They work slightly better than normal threads in Python. Did you try them and compare them with Greenlets?
Unfortunately, I haven't tried them,
okay.
So I cannot say anything about it.
Okay, basically they do things a little bit better, and sometimes it works the way you expect to, not having the GIL evil stuff going on. So,
okay, so they solved the GIL starvation problem, or what?
It bypassed something, and so. Actually, threads tends to execute better with the right amount of time you expect them to execute. So I recommend you to try them.
Okay, thanks.
You gave a fairly simple example using spawn. Now, for that simple example, you can do something very similar just using threading. And my question is, are there any advantages of using Greenlets besides just the things that you can see in threading? And also, when you start scaling up and you start getting a lot of threads, at about what point does it really start to pay to move to a larger, to move to something like Greenlets?
Mm-hmm. Well, first of all, your second question. I would say that memory is the limit for your threads. If you don't have any problems with the GIL, if that doesn't slow down your execution, then memory is going to start to be your border for number of threads you can have. The first question was, are there any other advantages of Greenlets? Well, the one I can think of is if you would like to use your own scheduler. So what happens is gEvent has a scheduler that's called Hub. And I'm fairly certain that runs Greenlets randomly. So if you have a specific pattern that you would like to implement in a scheduler, for instance, you have some Greenlets that you would like for them to run more often than others, you could use Greenless for that and write your own scheduler and precisely control who is going to run when. So yeah, that's one advantage.
So you mentioned that Eventlet was an alternative to gEvent. Does that still do the similar things with the monkey patching, the standard library, and all of that stuff?
I have no idea how Eventlet works, but I would say yes because it uses Greenlit beneath, so I don't see any other alternative to that.
Thanks.
Okay, thank you.
We got a